Hello, everyone, and thank you for attending WINLAB Research Review Fall 2022.
Here's the mic.
Yeah. Is that fine now? Okay. Thank you for attending WINLAB Research Review Fall 2022. My name is Shalini, and my talk will be on experimental evaluation of VR applications running on next-gen network scenario with edge cloud assistance. So starting with, we are almost every one of us are aware that VR technologies are gaining a lot of momentum gradually, and over the past few years in various sectors and industries, it has been able to grow a lot. And along with that, a lot of other verticals like the networking technology and the computing technology has been progressing to be able to support AR and VR technologies. So there are certain pros and cons which comes in with these sort of technology, which are kind of demanding to networking. And let's go over the pros first. It has great user experiences. It's applicable in numerous fields like the education sector, healthcare sector, communication sector, military operations, so on and so forth. And of course, improved view of facts and landscapes because you are taking in audio fields, visual fields, trying to artificially render it, create artificial visual environment, and great business opportunities. But then again, for the cons or the disadvantages that this kind of technology faces includes motion sickness if you don't adhere to the low latency requirement of these technologies, restricted movements in case you're trying to do some sort of huge processing or rendering at the user's end, which will limit your mobility. And again, the setup becomes a lot more expensive in that case. Now, on the contrary, if you want to get rid of the disadvantages of local rendering, you choose to do remote rendering. And with that, what comes into play is network delay because that becomes network dependent. So since we are talking more into local and remote rendering, just let us understand what's rendering. So it is the process of creating sensory images that depicts a virtual world. And these sensory images has to be produced in a continuous manner and not discrete events. So given that, if you're trying to do that rendering processing at the user's end, you end up with limited terminal processing capability because you're trying to do that rendering at, let's say, a handheld mobile device or an HMD, or at the most, what you can do is connect a PC to your HMD and try to render it. But again, what you get out of it is the gaming experience is poor and the control is also poor. And if you're using those CPU attached to your HMD kind of local rendering, the portability becomes an issue and it becomes costly. So to get away with that, people do choose remote rendering. And for remote rendering, you are basically offloading the process of rendering or the rendering technology off to a remote computation platform that could be an edge cloud or remote edge cloud, depending upon your latency requirement. And so when you do that, what we see here is it becomes dependent on the network conditions there. And it requires high bandwidth requirement to adhere to the latency numbers. And so to address to this kind of rendering and to get a great immersive experience, the motion to photon latency for AR/VR technology has to be less than 20 milliseconds. So the net takeaway from this particular slide is if you're choosing to do a remote rendering, it becomes network dependent. Now, since it is network dependent, we know that 5G and beyond networks, or whatever, 6G, 6G plus, and so on and so forth, they brought a lot of expectation to the market. And some of those expectations include very high data rate, 1 millisecond latency. I don't know if that is ever achievable. 10,000 times bandwidth per unit area, a lot more number of connected devices. And I think there are current reports on Cisco about the trillions or how many devices that gets connected until 2022. Along with that, an extended battery power for low power devices, 90% reduction in network energy usage, 100% coverage, and 5 nines on reliability. So a lot of things here, but we all know how much has been realized up until now. So therefore, since we're talking about uh, remote rendering and its network dependency, it's very important to understand the latency components which add to this sort of remote rendering and latency critical applications such as AR/VR technology. So since I have already introduced the term motion to photon latency, it is basically the time for a VR headset to respond to a user movement and to display the updated frame at the client's end. So this event includes T1 through T3 events. And to address this T1 to T3 events, a lot of previous literature has worked on parallel rendering, viewpoint predictions, as well as predictive rendering, all of that. So, but then as per our literature study, we have seen that network delay budget plays a very important role here. And the budget for that delay should be somewhere between 5 to 7 milliseconds. Therefore, to have something which is more realistic, we are doing this analysis of how much does this T1, T2, T3, T4, T5, T6 through T7 is adding up in terms of motion to photon latency. So another important factor here is the motion to MTP, which is motion to photon to motion to updated, which means as soon as any motion at the client's end in terms of the HMD or the handheld controllers are realized, how soon that is being sent over to the remote server for the rendering process. That's very important because that's going to determine a very important part of the latency, the network transport latency. And in our analysis, we'll see how the results explain that. And the target motion to photon latency is somewhere, has to be below 20 milliseconds so that the user is not able to perceive those delays and it doesn't experience any motion sickness. So the experimental objectives, which means that the way we try to address this problem or to work on certain limitation that we are talking up until now, is to build a framework, which we did to study the component of network latency and identify the network parameters which add to degrade this VR application. And with that, we did take an approach of prioritizing a traffic subflow, and we did achieve a QoE gain at the end. Following which, we tried to send a part of this traffic flow over TCP and then another part over the UDP to be able to adhere to the latency budget and to reduce resource consumption. And for to be able to realize this framework, we took help of NVIDIA Cloud XR client and server architecture. So it was backed by NVIDIA Cloud XR GPU technology. So this is typically the system architecture or the prototype that we created and ran our experiments on. So here the client is the Cloud XR client. The MEC server is also a Cloud XR NVIDIA MEC server. And I'll talk about the network bridge a little bit later, but let me just introduce the MEC server architecture. It's basically a Windows 10 machine backed by NVIDIA GPU. The Cloud XR presents a virtual HMD at the MEC server's end, so that the OpenVR application at the MEC server's end realizes that there is a virtual HMD available and doesn't mess around with the application at its application level. Along with that, it receives the control motions from the client side and then does the rendering, encoding, and sends it back to the client. Followed by the client architecture, which is again a Windows 10 client. It implements a SDK the software defined kit, software development kit. And what it does is it actually helps to do more powerful rendering for devices which have low power GPU hardwares. And so when the client actually connects to the server, it sends its specifications such as the resolution or the refresh rate off to the server, and then they sync and they work accordingly. Now comes in the network bridge. So setting up the network. So what do we do here? So initially, just to get an enhanced gaming experience, we try to play the game over a DFS Wi-Fi channel. And so that is basically a dynamic frequency selection, which uses underutilized interference channels. So basically what happens is when the access point boots up, it will try to scan for the less interfered channels. And with that, we used channel 100 with 80 megahertz. And with that, we were able to achieve 800 megabits per second as bitrate, and 90 frames per seconds were achieved, and we could play the game at its peak performance. Now we introduced the network bridge, and we did that, which is this portable Cosmos node, which is the access point. We did that so that we wanted to emulate network variability into this whole setup. And we did that with the help of NetEm. So this network bridge was imaged with NetEm, network emulator, and we introduced various synthetically varied various network parameters through that, which we'll discuss in the upcoming slides. So yeah, before we jump into the results, it's good to take a look at the experimental measurement objective. And the game that I was talking about, which didn't have a name up until now, so is Open Saber game. And this is kind of a fairly, let's say it has latency, it is latency sensitive, and it has some sort of space attached to it, which means these blocks keep on coming towards the gamer, and they have to slash it with the sword. Followed by the network parameters that we varied throughout the experiments, which is the delay, packet drop, packet rendering, and bandwidth. And these are the range over which it was varied. So we did two measurements, baseline measurements. We did it over public Wi-Fi, the WINLAB Wi-Fi, at the peak hours, and the DFS Wi-Fi, the DFS that I just spoke about, which does uses channel which has less interference. And so these are the two baseline comparison. Followed by the NetEm, which enables us to emulate diverse network condition by synthetically introducing these parameters that I mentioned there, the network parameter that are varied. And some pointers for the kind of experiment I carried out, which is each individual of these parameters were varied one at a time, which means if a delay was varied, we didn't vary none of the other three parameters. And so we try to take the study of individual parameter one at a time. And each experiment was run for 300 seconds over that many ranges. And most of the QoS parameters logs were collected at the client side. Now, moving on to the results. So the first set of results include a frame rate with bandwidth bottleneck introduced uplink, which is between the client and the server. So there is just one-way introduction of these variability of network parameters. And we see that initially a bit rate of 750 kbps is achieved with a resolution which is 640 times 360, which is kind of a medium quality video. Later on, when we were relaxing the bandwidth bottleneck through that synthetical NetEm access point, we got an 80% gain and achieved a bit rate of 3200 kbps, and that's the maximum the game demands. So, and we got a residue. It was an HD video that we achieved at 3200 kbps. Now, moving on to the FPS, which is frames per second achieved, and the frame time. So frame time CXR is just one-way latency between the client and the server. And we see that initially for the FPS frames per second during the bandwidth bottleneck when it was introduced. So we achieved somewhere around 77 frames and 78 frames per second approximately, and which later on relaxing the bandwidth bottleneck went up to around now 90 frames per second. Along with that, we also did another measurement for frame time CXR, and we see that finally on relaxing it, we got around 40 milliseconds of frame rate of frame time CXR. The next set of results includes varying the loss and the packet reordering. And a very simple observation was made out of here that more than packet loss, we see that the reordering is either performing similar to the loss condition, or else sometimes even worse than the loss condition. The reason is there is an addition, other than the network delay, there's an additional delay at the receiver's end. And so we see that at certain given point, it performs worse than packet loss introduction into the network. Followed by this, this is kind of a result which is obvious, but then this will allow us to give more insight into the next set of results. So here, let's say the control movement of the HMD or the handheld controllers, they are sent over TCP between the client and the server. And when the audio files or the video files are sent over or stream over to the client, they are done over UDP. So when we are doing this and we introduce this NetM delay, and by that, I mean if there is a surge in this T2 area, so delay surges. And what do we see here is the TCP times out and retransmission occurs. So of course, there will be a linear relation between the control latency, the NetM delay, also a retransmission rate and the NetM delay. So, and then, this effect is actually injected over the span of T2, T3, and T4, if you take a look there. Now, following this, we have an interesting observation such as this. So when we are introducing one-way latency uplink over the control traffic that is being sent from the client to the server, we see that there is a streaming latency delay. Remember, this streaming latency is basically the traffic or the audio-video files, encoded audio-video files, which are being sent from the server towards the client. And accordingly, we see it both the retransmission and this streaming latency have almost a similar relationship. So what we thought was, if we can prioritize one of this subflow over a slice, over a low latency slice, the other, the control, the streaming latency would actually reduce as well. And that's what we performed here. We reduced the NetM delay synthetically through the access point, and we see that the streaming latency reduces. So just one way, if we are trying to introduce a prioritization of this control flow, we achieve gain of QE at the user's end. So the future work for this prototype implementation, I would want to carry it over to a 3GPP compliant non-standalone 5G network. And we have started putting that together on a Cosmos testbed. We are using OAI for that. We are here, particular in this experiment, we just used one UE for recording these measurements, but we want to do it and follow it up with multiple PDU sessions, which means multiple connected UE. So some of these take-home messages include, we analyze the QoS parameters, which are affected by network variability for this VR gaming case. Our traffic subflow was prioritized and scheduled over a low latency network slice to achieve reduced streaming latency. And also we vary these network parameters to identify what are the key parameters which actually introduces or influences the VR QoE. So yeah, thank you for listening and open to any questions.
Thank you, Dr. Did you look into something called time warp? This technology to mitigate the motion sickness? Like, so you actually.
I think this Cloudixar has some sort of time.
Yeah, because it takes the latest position and motion data into account, and then it adjusts the latest frame, even though it was rendered with the old data, it will adjust it to the new data, so it kind of modifies the frame, right, to adapt, to try to adapt for it. So that kind of mitigates and makes the latency requirement a little less strict, right? And they even use it when you don't have a network, when you have local rendering.
I do remember when I ran that experiment, they had some component of time wrap, but I did explicitly break that down to see how much of that time wrap attributed to this.
Right. Yeah, you probably can't turn it off.
Yeah. They come with the package, so you have to do that.
Right.
Yeah. Thank you.
There's in one of the results, there's a very sharp improvement with the bit rate, and then it saturates it. Because it's rendered and there's no adaptation of the video.
So that saturates because after we are relaxing the bandwidth, that's the maximum it can go up. That's the peak bit rate for this particular kind of game for the Open Saber. So I think it was 3200 kbps, and that's the maximum. Yeah.
The game does not require.
No, it doesn't require it.
So it's surprising. There is no adaptation. It's the sharp degradation if it does the full bit rate.
Exactly.
What is the frames per second at that point?
At the peak, it is 89 or 90.
90.
Yeah, so we actually did the baseline measurement just to understand how well the game performs without any sort of network variability or any obstruction.
And if you reduce a frame per second, that causes all this. If you need to reduce, what would you reduce? The quality spatially or temporarily?
You mean the frames per second? So what we did was, if you need to reduce from the network side, if you are playing around with any of these parameters, let's say the bandwidth or the delay, mostly these two, they actually reduce them drastically. And that's why when I did with the public Wi-Fi, I got somewhere around 28 to 30 frames per second.